All right, so today we definitely want to talk about shortest path, especially shortest path algorithm, at least the introduction and some simple example. I would like to also continue with maybe the more difficult example tracing together with you, maybe in the tutorial session this Friday. So definitely you can assume we're gonna meet again in person this Friday. We're gonna do some interesting exercises together. Well, test one result has been released. Good to see you guys still. You stay, that's good. Awesome. Okay. Assignment number 2, I will release it next week. Okay, but we're gonna be fine. Okay. However many we can cover, I only test you on that, only that for the exam. Okay, but we do have some very good topics to discuss. Okay. Very quick recap. Okay, so last time we actually continued with the breadth-first search, just about how we can use a queue, FIFO queue, to actually trace the breadth-first search. So today, give you a little bit of heads up, we're going to talk about a shortest path algorithm. That one there is also going to use a queue. However, it's not the first in, first out queue. It's going to be something called priority queue, which you guys may have heard about from 2101. I'll give you some very quick background, and then when we get there, right? That's breadth-first search. And then we actually spoke about some exercises here. These are simple. I'll post a solution later. And for this one here, please try to continue with it and complete it. We'll try to pick it up from here, maybe on Friday to finish it, just to make sure it's complete for you. And then, okay. And then we'll talk about answering different graph questions about breadth-first search. All the questions have very similar answer compared with when you ask about depth-first search. Pretty much similar, except for the very last one about a cycle. I would like to talk about this particular one again. I don't think I did a very good job on Monday. I can do a little bit better today. Okay, so there's a table here just to talk about whenever if you got a directed graph and then you have a cross edge from breadth-first search, it doesn't necessarily mean you have a cycle. Okay, so that's something I would like to show you one more example. Okay, and then so that's just about how you can adapt the breadth-first search in counting how many connected components you have. So for your upcoming assignment number 2, we can definitely do some exercises on breadth-first search and also see some simple example about how you can adapt the breadth-first search for answering some graph question. I'll put it in the programming part so you can also see something that's working. Okay, okay, that's something I'd like to redo. So I thought it was a bit confusing from Monday. I'll do it again. And then we also started talking about a list, adjacency list strategy. So this will be the main focus together with adjacency matrix, either one or both of them for the assignment 2. So I'll just want to visualize it and then go over some critical parts to you, just to so that you got some conceptual idea before you actually have to do the assignments later. Okay, that's basically about it. Okay, let me now revisit this page right here. Okay, basically the same kind of setup. I want to go over the example a little bit more carefully. Okay, let's say we got these two, 1 and 2. These are undirected graph. And these two over here are directed graphs. As you can see, we got arrows. I would like to actually perform DFS versus BFS and see what we can get from there. Let's start with the undirected graph right here. Okay, right here. If you do the depth-first search, of course, you're going to go A to B. Okay, maybe thinner. A to B, and then B to C. So far, discovery. And then as soon as you go from C to A, you basically got a back edge. So the path that leads you to that back edge forms a cycle. Always the case. All right, let's write it down. So the observation so far is the path leading to a back edge denotes a cycle, always. And of course, in this graph here, it's undirected. Okay, let's now try to do undirected graph as well, but BFS. Okay, let's try. Okay, of course, Josh, you can correct me if I got any mistake. Right, so here I got A to B, right? A to C, and also A to D. I have just reached out to level number 1. And then when I do B here, B should be connected to C, right? So right here, I have a cross edge. I'm basically connecting between B and C at level 1, right? And this one here, you can think about the path leading to this particular cross edge can also give you somehow like a cycle, right? That's also giving you a cycle right here, okay? So this one here, you can think about right here. So let me also write it down. The path also somehow leading to a cross edge also imply or denote, doesn't matter, I'm just changing the wording. There's a cycle. Okay, so this is also undirected. Let's now, so for in the case where you got undirected graph, doesn't matter if you have found a cross edge or back edge. That simply means you got a cycle, right? Let's now talk about directed graph. So let's talk about these two, 1 and 2 over here. Let's follow the arrow, okay? So you can see that for in the vertex A, we only have to go out by these two edges. This one here is incoming, so we don't really go out by that, right? So just notice the difference here since we got arrows. So now for depth first search, let's see what's going to happen. So we actually have right here A to B and then B to C. And now for C here, we don't really go to A anymore because the direction is different, right? It's actually coming here. Right? And then we go for C to D. And then, so now for D here, there's only one option. We go D to A. So now we are going to a back edge again, right here. All right? So the path that's leading us to a back edge, which is A, B, C, D, A, is a cycle. All right? So in the case of the depth first search, when you apply that on the direct graph, it's also going to give you a cycle. Okay, so here you can also say finding a back edge implies there exists a cycle. Similar, right? The same point. Now, let's now take a look at breadth first search, but on a particular directed graph. Let's see what's going to happen. So here, if you see that, if I only do A and B, right here, A, B here, and also AC, right? That's about reaching out from level 0 to level 1. And then here, I have a cross edge. You can see now the path that's involved right here does not represent a cycle because it's really from A to B, B to C, but you don't really have a way to go back. It's not a cycle. So this involved path does not represent a cycle. So it's not always the case. Okay, I'll write it down and then I'll make one more point. So finding a cross edge not necessarily means there exists a cycle. But there is a cycle here, really, because if you see that here, if you follow A, B, B, C, C, D, and back to A, so somehow this can give you a cycle. Of course, that simply means for breadth first search on the directed graph, you cannot just use the existence of a cross edge to tell you that there's a cycle. All right? Exactly how to adapt like a breadth first search to find a cycle, we may cover that a little bit later, but just know at least the basic facts. Let me recap, okay? And then we can revisit this maybe later in any review session. We are saying the following. When you do breadth first search, either on a undirected or directed graph, every time you find a back edge, always it implies there's a cycle. Right? In the case of doing breadth first search, if you're doing that on an undirected graph and you find a cross edge, it also means you have a cycle. However, in the case where you're doing breadth first search on a directed graph, finding a cross edge not necessarily mean you have a cycle. As we can see, this example here tells us it's not always the case. Right? All right, question. Okay, just remember this property, that's important. So that's why typically if you really want to check to see if there's a cycle in your graph, you will typically try to do depth first search to make it very general, unless you know beforehand your graph is undirected. Otherwise, to make it general, you should always try to adapt your depth first search to find if this is a cycle by finding this back edge. All right. Okay, so if that's good, let's now move on a bit. Okay, the adjacency list strategy. So this will be something I definitely would like to have you experience, maybe in the assignment number 2. I think today I will just talk about adjacency list. There's one more strategy, which is called adjacency matrix. If you remember back in week number 1, we can have you guys that have done some exercise on like a 2D array. So that one is going to be handy actually for the third strategy. So once we cover all the 3 common strategies for implementing the graph, I'll also do a table to really compare them. Okay, that we'll do a little bit later. But let's just now try to get hands-on experience for one of them, each one of them. So now here, I would like to keep this one handy here. I'll go back and forth. So this is really the Java classes you have. Okay, let me remind you very quickly. So we have a class called adjacency list graph right here. And then we still have list of vertices and list of edges. So we've got to use doubly linked list, doubly linked list. So this part here is just the same as before. Okay? And then for individual vertex, we got element. And also, vertex also got a pointer back to the list of vertices. This one here is just the same as edge list graph. What we are adding in addition, in the case of adjacency list strategy, is for each vertex, we try to include something called incident edges, which we'll visualize. So for every vertex, you also, let's say, if I got a vertex like this, you got 1, 2, and 3. 3 incident edges. In that case, all 3 of them should be stored as a collection in the vertex itself as well, which is something we didn't have in the edge list graph. Okay, that's something we'll visualize. That's something you want to pay attention to. Okay. What about the edge? For the edge here, we still have origin, destination element, and also the position of the edge back to the list of edges. So we can have constant time of deletion of the edge. And what we're adding more is about where the edge is in the corresponding origin and destination vertices, incident edges. That's something we'll see. Okay, you're also going to point back. So whenever we got this kind of position that go back to the original list, it's just for efficient deletion of the object itself. Okay, we'll see. Okay. So that's an overview about something you want to pay attention to. Of course, in your assignment number 2, I will try to collapse all these 3 into a single class for you. So you don't really have to really see that many classes for inheritance. So just something to heads up. Okay. All right, let's now take a look at this. All right. Adjacency list, in some ways, a little bit more complicated than edge list graph, a little bit, but it's not too bad. Okay, let's now take a look at what we have. This is conceptually the graph we are trying to build, right? We got 1, 2, and 3 vertices. We got 2 edges right here. Let's now review what we know already. All right, so what we have is, let's say, first of all, we have the list of vertices. So we got vertices, and also we got edges. Let's see the correspondence. Right here, we got a list of vertices right here. And also we got a list of edges right here. All right, that one's straightforward. And then let's look at how about just the vertex itself. For each vertex, let's now start with something we already know from edge list graph. You can see for vertex, we got element, that's okay, but we got the vertex list position. What does that correspond to, right? So now you can see that right here. For this particular vertex, for example, let's say vertex B, that corresponds to position 1 in this list. So this pointer here is really corresponding to it. And also vertex 1, vertex A, and also vertex C. So that's the position. All right? Similarly, if you look at the edge list, the edge, also we got edge list position. Okay, that one there also correspond to, you can see we got 1 edge objects, the second edge objects, they also point back to the list. So this will be 1 here and also 1 here. All right, nothing new so far. It's really about we are extending the edge list graph. Okay. All right, and then let's now move on. Let's now talk about this particular one, incident edges. Okay, let's see that one. That one's important, okay? So this one here is going to be a doubly linked list of edges, basically. So now let's say, for example, if you see A here, it has 1 and 2 incident edges. If I go to vertex A here, it points to a collection with 2 edges. One of them is O, the other one is P, basically. All right? So I'm going to highlight just this list right here. That's the incident edges list that we have right here. All right? And similarly, you can see for B here, it's a different list. You can see for B here, there's only 1 edge incident to it. In that way, the list of size will just be 1 as opposed to 2, right? And also similarly, you also got incident edges for C as well. So depending on the degree of the vertex, if you guys recall, the degree of a vertex is how many incident edges it contains. So the size of the incident edges list corresponds to the degree of that particular vertex. So that one there we will see later can also impact about the running time that we're going to perform some graph operations. But I'll get there a little bit later. Just remember, when you actually talk about this strategy here, the degree of each individual vertex is important because that's going to impact the size of the corresponding incident edges list size. Okay? So we got 1 incident edge, 3 of them. All right. Okay. And then let's now talk about something also what we knew from earlier. Okay, how about this one here? So how about blue? You can see for each edge we got origin and destination. Let's identify them. Okay. So now you can see, for example, for edge O, origin here. Oh, sorry, let me say it again. O here, we got origin over here. And also we got destination. Let me see what I have. Let me just see origin. Okay, sorry, I just confused myself. My apology. You can see O here, and then we got one is origin, the other one is destination. These 2 pointers, right? Let's say O here, A here, and B here. Okay, let me just write this down specifically. So in this case, we're saying this is the origin. This is the destination as far as O is concerned. Okay, so you can think about what we have here. Let me just see the blue. There is one pointing to B. There is another one pointing to A. So one is origin, the other one is destination. Origin and then destination. All right. Similarly, for P, also origin and destination, etc. Okay, so that one there. You can think about this A here will be origin, and this will be destination. Okay, you see the idea, right? All right, so we only got one thing left, which is about the position back. So here you can see that here we are trying to do, for each edge, you also need to know where you are in your origin and destination's position. Okay, let's see what this really means. So if you actually look at here, let's say this one here and this one here. Let me highlight them first, and then I will make some annotation for you right here. Okay, so you can think about this one here. This one specifically is about edge O's position in its origin, and its origin here is B. Incident edges. But in this case, it's only one node over there, so only one position, point back. So if you really want to, at some point, remove edge O, you have to remove this edge here from this list over here. You have to, right? That's something you will have to do in the assignments. Similarly, you can think about the second pointer here, right here. Okay, I'll put it here. So that one there, in a very similar way. So that's edge O's position in its destinations, and its destination here is actually A, right here. Okay, we're pointing to this particular list. Incident edges list. So this diagram here somehow is very, in some ways, really abstract, but it really summarizes all the pointers you're supposed to be aware of when you actually program the adjacency list graph. Okay. All right, so try to look at this diagram here and also convince yourself they really have the correspondence in all these stuff right here, okay, from before. Okay, and you'll be conceptually ready for assignment 2, at least for this strategy. I'll just give you guys maybe similar methods to implement again, just to get used to the data structure. And then I'll give you some additional ones to say, given some Bradford search, how can we adapt it to answer some simple graph question? I'll give you 1 or 2 so you can see the idea. So guys, question? Okay, all right, good. Still very conceptual. Of course, you got to get your hands dirty, assignment 2, to really see how things will work. But we'll look forward to it. All right, if no question here, I would suggest we move on to some very exciting topic. Okay, so I want to talk about Dijkstra algorithm for calculating the shortest path, but let's now do some foundational work. Let's define a new kind of graph. That one there is called weighted graph. Okay, so there are slides. Let me show to you if you want to look at the slides right now. It's going to be 51 and 52, but I'm going to summarize the key points right here. Okay, but I'll see if there's anything missing. I will also add it. Okay, let's now talk about it from scratch. So this is one example of a weighted graph. It's more like a flight, like an itinerary, between just happen to be the U.S. Airports. So I believe Boston, New York, and also Miami, not too sure, L.A., San Francisco, etc. Right? Just different. It's a very simplistic routes. Okay, let's now define different terms. Let's start with the most basic units when you talk about weighted graph, right? Weighted. And then we're going to define what the shortest path is in just one moment, right here. All right, let's look at the first term, weights. So weights. Whenever you talk about the weights, they're somehow associated with certain cost. Could be the distance you have to travel, or maybe about, I don't know how much bandwidth it's going to cost, right? So it depends, it's some certain cost that has to, so you always want the shortest one, like the minimum one that's going to save you the cost as much as possible. Whenever we talk about weights, it's going to be defined on edges. I'll give you an example in a moment. But for example, the notation is you're going to use the lowercase w for weights. And then you're going to specify an edge, a single edge. If you remember to specify an edge, you're going to say the origin and destination. Okay? So it's going to be U and V, for example, vertices. Okay? That's a notation. Okay? I'm going to highlight it. Because all these concepts we're going to mention in this page here, they're going to be used in the Dijkstra algorithm. So let's now make sure they are clear. So one example. Here, for example, you can see that let's say from Boston to Miami, right here. Right? You can see there is some certain weights. And of course, usually with the weights, we just put some numerical value. We don't really specify what units they are. There will be some implicit assumption. For example, it could be about miles or kilometers. I'm not too sure. Maybe miles. Okay. So here, example, you can say the weights of from Boston to Miami. That one is equal to 1258. Okay. And there's some assumption we are making. Although there exists algorithm to really find out the shortest path when you actually got negative weights on the graph. But that's not the algorithm we're going to talk about. I'll give you some remark and some further reference, but for this course, we're not going to address them. Right? It just requires certain small extension. So we have the following assumption. So the weight value, always non-negative. Can be 0, but cannot be negative. Okay, very important assumption. Also later on, either today or maybe next Monday, I will explain, I'll also show to you, what if this assumption here is relaxed? It's actually going to cause the Dijkstra algorithm not to work properly. That's something we also need to understand. May not be today, but maybe Monday. Okay. So that one is something also very important, fundamental about the assumption. So the first concept is about the weights. And then let's now talk about the length and weights of a path. So now we're extending the concept about edges into path. Okay. So let's now use a different color. So we talk about the length. Or we can say the weights of a path. So now right here, the unit's a little bit different. It used to be on edges, but it's now on path. Okay, let's now try to do some notation derivation here. And we're going to use the same letter W. So think about we are overloading the letter W for two different purposes. But usually it should be quite clear in the context which one you really mean. You can simply see whether the W is applied to two vertices or is applied to a series of vertices, in which case it's a path, right? So it should be rather clear, usually in the context. So I'm going to put W here. Okay. Now, what I'm going to put here is going to be a path. Okay. In general, the path is going to be a list of vertices. I can say vertex 0, vertex 1, all the way to vertex k. Okay? So think about just this part alone. Just this part. This is a path with k plus 1 vertices. Would you agree? It's k plus 1, right? You start from 0 all the way to k, right? So, and then also you gotta make sure you remember the W here and the W here, they don't really mean the same thing, but they can't kind of relate it, okay? You just overload it using the Java term. All right. And then what does it really mean? When we want to calculate a weight or a length, in order to do that, we have to use the W here more like a helper function or helper method, okay? To do that, we're going to say this will be equal to, individually, the weights of the edge between V0 and V1 plus the weights between V1 and also V2 plus all the way to, guys, what should be the last weight I should put in the equation? What will be the last one? Huh? K minus 1 and K, right? Exactly, right? Just see the pattern. Very good. So it's going to be V, K minus 1, and V, also K. I think that this kind of notation will be very important because I think I also want to give you guys a chance to try to somehow do some inductive proof. But this time, we'll try to apply inductive proof, not just about property of the graph, but rather we may want to try to prove about the correctness of the algorithm. That's something we would like to try as well. So you got different exposure to the method. Okay. Okay, so think about right here, the W here is really to calculate the weights of an edge. Weight of an edge. So in order to calculate the weight of a path, we're going to individually sum up the weights of individual edges. That's what we're doing. All right. Let's now, again, simplify the notation. That's something you will see quite often also in the literature. We can use a sigma notation. Okay, sigma here. Very easy to work out because you can see that you actually got indices 0 here, 1 here, all the way to k minus 1, right? And always the other way, The other end is just 1, 2, exactly plus 1. So what we can do is, so starting from 0 all the way to k minus 1. And then we're calculating the weights. Vi plus 1. Right? We're just patternizing what's there. So this will be the equation you actually saw on the slides. I just want to derive it together with you, just to make sure you're feeling comfortable about it. That's what we meant by the length or weights of a particular path. All right? The next concept is to say, between two vertices in a complicated graph, there might be more than one path that can connect them. In that case, we can calculate various values for length or weights of different paths that can connect the two vertices. And then we want to select the minimum one. For example, let's say in this case, let me give you the example first. Let's say I'm choosing two cities. Let's say I have chosen, let's just make sure. Let's say, how about JFK? And also LA. There are different paths we can go. For example, you can either go to right here, go to here, go to here. Or you can go here, go to here, go there, go here. Okay, just one more. You can go here, go here, go here, and go here, and go here. There are many paths, basically, right? Among all the paths, we want to find the minimum one, which means the summation of all the weights in the path components, like edges, should be the minimum value. Okay, that's something we want to decide. As you can see, even given this particular graph, to really see that manually is not that easy. You definitely need some systematic way to really compute it. That's something we want to learn today. Okay? So the last concept is called distance or shortest path. Distance or shortest path. And usually when we say this, we actually got the context of two vertices, between two vertices. Two vertices. All right. So this one here, distance and shortest path between two vertices. And of course, the unit here is about between two vertices. Right? So let's now put a definition, and then we'll talk about some special case in the notation. So we are basically saying, out of all paths connecting two vertices, let's say U and V. And the notation goes like a lower d. Be careful. We're going to end up using lower d and capital D. So lower d here is really about the shortest path. Okay, be careful. Okay, so we say lower d between U and V. So this one here denotes the minimum length or weights among them. So you can think about the length and weights I'm talking about right here is really the length and weight I spoke about earlier. We are really building up the notation, right? So I think after today, I think maybe over the weekend, try to revisit these concepts. It's going to help a lot, right? Okay. And we are choosing the minimum. And the notation here is about lower d between U and V. Okay. Let's see, there will be some edge case. You also got to remember, what if there's no path between two vertices? In that case, what should we do? Let's say, for example, I don't know. Let's say for whatever reason, Do you remember the short name for Pearson? Is it YYZ? Yeah, okay. Let's say somehow we have no flight supported here. In some way, we are isolated. In that way, how do we define the distance between YYZ and Boston? What should be the distance then? There's a special value. -1. Good guess? No. Thinking this way, because our goal is to calculate like a shortest path, like a minimum weights, right? In that way, if there's no connection flight between Toronto and Boston, that should never be chosen. Infinity, plus infinity, or minus infinity? You're guessing, or? Yeah. Okay, yeah, it's good guess, yeah, plus infinity. Because plus infinity will guarantee there's always going to be something that's better that will be chosen, conceptually, right? Good. Okay, if there's no path between them, so here. So special case. Special case is also very important. So D of U and V over here is going to be plus infinity if they are not connected at all. All right, so I'm going to put example here. Let's say example 1. If I say the lower D between Toronto and also Boston, that one there, just infinity. All right, there's one example on the slide. I can also quote it. So the shortest path between, let's say, JFK and also LA. Okay, that one turns out to be the sum of, you can do the math, go from here, go from here to here, from here to here, and also from here to here. That turns out to be the shortest one. Josh?
How would you implement infinity programmatically?
You can say maybe the maximum of integer, for example, right? I think that would be a reasonable choice. Yeah. Or if for some reason you kind of know the range of the weights for your graph, you can just say whatever maximum it is plus 1. That's also fine. Yeah. Good. All right. That's a good question, actually. So I think this one here is going to be, okay, you can do the math, please. I didn't have that number. So it's going to be this plus this plus this, right? It's going to be that number. Okay. You can calculate. And also, you can also convince yourself, for example, if you find an alternative path. If I go from JFK to Miami and then Miami to this city here, so the added up value, the sum of the weights, this plus this plus this will be more than this number. You can double check, okay? Anyway, so you get the idea. So guys, question? All good? All right. I would suggest we take a short break, and then after the break, we're going to dive into the Dijkstra algorithm. All right? I think today, I don't want to go like a very complicated example. I want to go over only 2 simple ones and dive completely details into it to show you what you should really pay attention to. But we're going to do the complicated one on Friday when we meet up in the tutorial. Okay? Please get your iClicker ready, and then we'll take a short break. Okay. So before the break, we went through slide number 51 and also 52. All right, you guys can, again, just review it. Everything has been covered. So now for the Dijkstra algorithm. So I would suggest for today, we got about less than 30 minutes. We'll do a very quick first pass just to see the, like a bullet point form, a little bit informal, not really in Java. I think that should be enough for us to get some basic intuition. I'll go over that with you step by step. Don't be too frustrated if you get very confused about certain calculation there. But I would suggest after a very quick first pass, we'll try to do 2 simple examples to see how that can be used. And then when we meet each other again on Friday, we can try to do some complicated one together. And then I'll give you another one for assignment number 2. So you do definitely get enough practice for Dijkstra algorithm. But if you want to use ChatGPT, maybe Google, you can always find lots of examples about calculating shortest path using a Dijkstra algorithm. It's definitely everywhere. But at least I'll give you several examples. And then after that, maybe next Monday, I would like to talk about two important things about Dijkstra algorithms as well, which is about running time. Okay, we're going to do that. And also we're going to talk about why the Dijkstra algorithm wouldn't accept any negative weights. Okay, we're going to see how that can fail. And then I'll point out to you some reference about then what kind of algorithm should you use if the weights in your graph may be negative. Okay, let's now talk about it. Okay, the actual algorithm basically is not very long. Just about like that. Okay, but let's go over that. Okay, let's see. Okay, I'll try to visualize certain part here, but it's only a first pass, right? Let's see what we can do. See, it's an iterative algorithm, right? Double nested loop, basically. So there will be initially, before the loop, we gotta do some setup. Initially. So, okay, let me be a little bit thinner. So before the loop, we actually got to do some setup. And in order to really keep it going, you have to remember there are two variables you have to keep updating throughout the course of the algorithm. Okay? One is called, be careful, capital D rather than lower d. Okay? A here stands for ancestor. We'll talk about exactly how to use them. Okay, we'll see example. But these two variables, we should keep updating them. Pretty much like for breadth first search or depth first search, you got to start with some source vertex. You got to start with something. Okay, so we call that the source vertex. Okay, let's say if that one is S, right? For example, let's say if you somehow want to calculate the shortest path from Boston to every other vertex in the graph. In that way, this should be the starting point, Boston. If you want to calculate the shortest path from San Francisco to every other city in the map, in that way, you should really start with this instead, right? The very nice feature about Dijkstra algorithm is once you complete it, it's going to give you the shortest path from every other vertex from this particular single source. It's a very powerful algorithm, all right? That's something we'll see. So we're going to keep updating D and A, okay? So D here, let's emphasize that the D here, right here, is more like the shortest path so far. Shortest path of some vertex so far. You can think about eventually it's going to get exactly equal to the lower D, which is a genuine or true shortest path. Eventually, upon completion of the algorithm, the D of any vertex, capital D, will be equal to the lower D of V. Okay, again, think about this is more like an intermediate result in the loop. Intermediate result in the loop. And this one here is the true shortest path we want to get to. Shortest length to get to, eventually. All right, just be careful about lower D and capital D. They definitely mean something very different. They're connected, but not exactly the same. And also about ancestor. So also we're going to use the ancestor variable to also work out exactly what the shortest path is. Well, I'll show you that as well. Okay, and then we have to use a ADT called priority queue. And to really implement priority queue, a very common way of doing it. So back in 2101, so if you took it with me, for example, we talk about there are different ways you can really implement priority queue. You can use a linked list. We can use an array, like a linear data structure. But that one there is not going to give you very satisfactory runtime. I can maybe do some summary, maybe a little bit later. But the most efficient way to really implement priority queue, any idea? If you can recall any information, that's okay. If you recall, yeah.
Circular array?
Circular array? No. It's all still linear. To really implement priority queue efficiently, you need a non-linear data structure. A heap. All right. All right, I'll write it down first, right? We have to revisit some information there. We may not get a chance to really cover complete details, but at least for your information, okay? So if you want to support this priority queue, right? It's going to be using a heap. A heap is basically a balanced binary search tree which satisfy the so-called structural and relational property. But don't worry, since we haven't got a chance to review it, so I think I'll just give you the facts you're supposed to know at this point, right? I can supply some references for you, maybe later, okay? But for now, just imagine that we have a priority queue, conceptually. And whenever we have a heap, we are really interested in extracting the entry with the minimum key. Minimum key heap. And the key we are using is the D value. What is the shortest path value so far? That's minimum. That's something we'll see. All right, just pay attention to the different aspect for the algorithm. Okay, and then we put all the vertices into priority queue. And then we're going to keep extracting one at a time. Every time we extract, we're going to extract the vertex with the minimum D value. That's what I'm going to do. Okay? And then from step number 2 is like a while loop. Right here. There's one here. Remember, we just added all the vertices into Q. So initially, Q got all the vertices in there. We're going to keep processing it. At the end of each iteration, we're going to remove exactly one vertex once we have already processed that. And we say that once we remove a particular vertex, we also say it is visited. Okay? So once you have already removed a particular vertex, we say that it's visited. It's a slightly different notion about visiting a vertex, not just about you see that vertex, but you already have processed that and remove it from the priority queue. Okay, that's something we'll see as well. Right, let's see very quickly just about the different steps in the loop. So here we're going to see number 1. We're actually going to, okay. You want to find the vertex with the minimum D value. What does that mean? Okay, visually. Imagine that this is your queue, priority queue. Imagine that. Priority queue. You got many vertices there. You got many vertices. And one of them is simply just U. Somehow you got a way to really extract U with the minimum key value, which is D value. Okay, we're going to pick it up. So U here has the minimum D value. U here is such that the capital D, the shortest path so far we have calculated for U, is the minimum. We do that, all right? Is the minimum among all the other vertices. We just pick this one here. When there are more than one vertex which has the same minimum value, you can pick either one of them. Okay, doesn't matter. Okay. So that's really what this is saying. And then you can see there's another loop right here. For every vertex that's adjacent to it. Quick question for you. For this part here, we say for every vertex that's adjacent to U. So basically about, let's say this is U, all the vertices adjacent to it, we got to look at them. How many iterations do we expect to see maximum for this loop here? How many? Can you express that using the term? That's something we actually just said earlier. Ah, very good, exactly. All right, very good. Yeah, you see, all these concepts you're gonna be synthesized, this algorithm here, okay? So think about right here. Let me just use a different color, okay, right here. So this part here, just this part, okay? This part here, the number of iterations, I would say less than or equal to, not exactly equal to. This is very important. I'll explain why. But this is very important for you to remember. This Dijkstra algorithm is very efficient, as we'll see later. If somehow you want to really go for all the incident edges connected to this particular U, then the algorithm will be much more expensive. Okay, so that's something you want to keep in mind. Okay, less than or equal to the degree of U. Okay, let me also make that point right away. Often, it's not necessary to go over all the incident edges, which is very time consuming. If the graph is complete. Do you remember the definition of being complete? What does it really mean if my graph is complete? Anybody? You remember? Back in the definition, for test 1. What does it really mean? If I got, let's say, all right, that's something you guys will have to also recall. Complete, right? Here, that means the number of edges, what's the upper bound? Big O of V squared, right? Remember? Okay. Number of vertices squared. Okay, just remember. Okay, that's something we said about. You can definitely recall. All right. Okay, I'll leave that to you. Okay, let's see roughly what we're going to do here. Okay, what we're saying is, let's visualize what's happening here. So what we have is this. So now imagine that we have U and, right, we got V here, and we got U here. Okay. So here we got U, which has the minimum D value. And then we are looking at one of its neighbors, one of them, V. I will just highlight it for now. It is important for you to know here, the V here must be in the Q. Oh, sorry, must be not in the Q. I think I maybe put this definition wrong. Sorry, I beg your pardon. So this one here, that should be, remember, I'll fix it, right? I just got it wrong terribly, okay? You gotta make sure you only consider your neighbor if your neighbor is still in the queue. If your neighbor is already out of the queue, that means you don't need to touch it. So this is saying you don't really have to visit all the neighbors all the time. You only have to choose those neighbors that have been already, that are still in the priority queue, okay? So here, the V should still be a member of the queue. It should still be there. Okay, I'll make sure I fix this, right? Just it should be a member of, not a member of. Okay. And then you can imagine that we have certain value here. We got D of U right here. And then we have a weight. So this is the weight between U and V. And there is some D value as well for V, which is D of V. So we got this one here, we got this one here, and we got this one here, right? This equation here, it's a little bit like, when you want to find out what's the minimum value in the array. Let's say we set the first element to be the minimum, and minimum so far. You're basically comparing the minimum so far with the current element. If the current element is smaller than the minimum so far, replace it, right? We're doing something exactly the same. So what we're saying is, if somehow this value plus this value is strictly smaller than this value here, then we update this value to be that smaller value. That's what we're saying. Okay, so you can look at the equation a little bit later, but we're going to do example. Okay, so here we're going to say right here. So this will be updated to D of U plus the weights of u and v if necessary. Okay, so this will be the condition. Okay, we'll look at that later. Okay, so in that case, you're going to set the d value and set the ancestor. Okay, and that's it. That's the algorithm. Okay, not too many steps really, but to really see exactly how that works, and later on to see the running time and also to prove its correctness is not trivial. That's something we're going to spend some time discussing. Okay. So what we would know is upon the completion of the Dijkstra algorithm, then for every vertex, we will get exactly the d value, that's the final one, is exactly the shortest path between that particular vertex and the source. That's something we'll see. Okay, we're going to calculate many results at one go. And then we are just going to do a little bit trick about reversing the ancestor, and then we'll get the shortest path as well. I'll show you that too. Okay. Anything you want me to clarify right away before we see example? We're going to do example for sure. All right, let's now do example. First one, simple. Okay. This one is even trivial, but I want to use that to really show to you about the different phases. Let's start with this one here. Okay. And I would suggest maybe it would be the best to help the tracing if we draw a table. Okay, let's do it this way. Okay, so here we're going to say trace which iteration we are in. Iteration. Okay, and then we are going to talk about what is the vertex that we pick with the minimum d value. Okay. And over here, what are the changes we make, if any? Okay, let's keep track. Now, initialization. Initialization, let me just put in gray. Before the loop, init. Okay, let's start with that. Okay, so these two are not applicable. Let's see the setup. For each vertex, we're going to do D, capital D, and also lower a, ancestor. Ancestor is straightforward. We use the, a ancestor of W. In the textbook I use, it's called neo, like a null. Neo is more like a null value in other programming language in the old days. For example, if you program in Lisp, or maybe you do, I don't know, if you ever program in Lisp, it's more like another functional programming language. They use the neo to say it's null. Just think about it's nothing, right? Just no meaningful value just yet. So the ancestor for every vertex to start with is simply neo. Oh, sorry, here. So that will be the ancestor for x is also neo. And the ancestor for y is also neo. The ancestor for z is also neo. Straightforward. And now the capital D value. Question?
So what does neo mean? Is it
like a null.
Is it null, but is it not the same thing?
You can think about they're really the same thing, but neo is just like undefined. How about that? We're just saying in the beginning, even before we start running the algorithm, the ancestor for every vertex is simply undefined. That's what we're saying. But we're going to keep updating them as we go. Okay, just for now. If you say null, conceptually, I'll be okay with it. Just undefined. Okay. It's a valid question. But if you ever program in Lisp, for example, it's a programming language. It actually has lots of neos. Okay. Okay, just in case you're still not feeling comfortable, I'll just say that one simply means undefined. Okay, right here. Okay, let's talk about capital D. For capital D, it's going to be like only, we're going to start with, by the way, we're going to start with W. Okay, so this is starting point. It's very important. Only the starting vertex is going to have the capital D value being 0. Okay? D of W, 0. The capital D value for everything else will be plus infinity. So that will guarantee when we first pick the minimum D value, which one will we pick? W, the guarantee, the starting point. Okay? So the capital D of x infinity. You know what? I'll write it a little bit downside so you will see that, because we're going to keep updating it. Capital D for x will be plus infinity. And capital D for y plus infinity. Capital D for z infinity. That's the initial setup. All right. And for the first iteration, let's now put iteration number. We're actually going to, let me start with maybe blue. Iteration number 1. Right? Think about, we also got a Q right here. Okay, we got a Q here. So Q right here. So in the beginning, we also put all the vertices there. So we're going to put W, X, Y, Z. In some way, the order of the Q doesn't really matter, because you only pick them depending on the D value, that whichever that's minimum, okay? Priority queue. So now for iteration number 1, we're going to pick W. Okay, W is going to be picked. And then let me now try to visualize it like that. So W is now picked. Okay, so we pick W. So if you revisit very quickly, what we said earlier, once you pick that W, W is a bit like the U. That's the minimum, right? And then we want to find all the vertices adjacent to W, which is X, Y, and Z. And then for each one of them, we're going to check to see whether they still exist in the Q. All of them are. And then we're going to check to see whether this equation is going to hold, which I'll write it down for you. If they are, we're going to do some changes. All right, let's now do that. Here, X, Y, and Z, all of them are still in the Q. So they passed the first check. Good. And then let's now try to see this. Well, we can do some detailed reasoning here. You can think about, this is the weights, and this is the current weights. We are basically comparing right here. Oh, somehow I missed that. 0, right? Okay. 0 plus 40 compared with plus infinity. Which one is smaller? 40. Update this by 40. That's what we're doing. All right? So here, we're going to say like this. So D of W plus the weights between W and X is strictly less than the D of X. Okay? So D of W is 0. The weights between these two vertices, 40. And then D of the X, nil. Oh, sorry, plus infinity. And this less than holds. So now we're going to do 2 updates. What we do is, we're going to say, update number 1. We're going to say D of X will be equal to 40. Change that to 40. And then we're also going to change the ancestor to be W. And the ancestor of X is simply W. Right? Similar reasoning you can also see, right? I'm just going to complete them, all the changes. So here you can see 0 plus 30 less than infinity. We're going to update that as well to be 30. And also 0 plus 20, also less than plus infinity. We're also going to update it, right? So let's do that. So change this one to be 30, update it to W. Change this one to be 20, and update it to W. Okay, write it down. So D of Y is 30. A of Y is W. D of Z is 20. And A of Z is W. Okay? like that. That's the first iteration, okay? After the first iteration, what should we do? We should remove the vertex from the queue, right? So we're going to remove it, okay? So now we're going to remove it, okay? That's the first one to be removed. Now, second iteration, all right? There will be another 3 iterations, I can tell you. 2, 3, and 4. Okay? So now for iteration number 2, which vertex should we pick? Any idea? Z? How come? 20, 30, 40. Minimum 20. Good? Yeah, exactly. Exactly the reason. So pick Z. Where D of Z was Z is equal to 20. All right? Once you pick it, now the question is, do we do any change? So think about what's going to happen here. Y here has the incident edge to W right here. W is the only one. However, is W still in the queue? No. So it fell this condition here already. So realistically, think about this. Let's draw a little bit of connection to Java. Here, I can easily use %. Remember short circuit evaluation in Java, right? So if this one here is already false, I don't even bother to check, right? So you only check this condition here when the vertex you're talking about is still in the queue. If it is not, you don't really do it. There are also another alternative. Rather than checking to see if the vertex is really in the queue, you can mark to see whether the vertex is visited. So as soon as you remove a particular vertex from the queue, you can mark that attribute to be maybe true for being visited. So you got option there, right? Depends on how you implement it, okay? All right, that's good. So changes, no change. No change because W not in the queue. All right, now after this, remove Z. So that'll be the second one to remove. And of course, there's a second one to consider as well. Okay? And then we're now going to go to next one, minimum. Should be Y. Agree? Compare 30 and 40. And then, so after that, we're going to do Y. The D of Y is actually equal to 30. Also, no change, because the only neighbor for Y is W, but that one is not in the queue, right? So we don't even bother. So because W is not in the queue. Okay, number 4 is about X, right? Give me just 2 minutes, and then I will conclude this example, and then we'll continue from Friday. Do more example. And then over here, that'll be X. And D of X right now is 20. Also, no change because the W is not in the queue. Okay, just give me 2 minutes, please. Okay. So now, that's everything we have. Let's see what we got. Let's try to interpret the result from the algorithm. So now here, this is the source. Everything else is something we can interpret. Okay? So now let's say here for X. Okay? Let's just say for X. You do something similar for Y and Z. Okay? Let's now try to interpret that. Okay? So this one is saying 40 is the weights of the shortest path to go from the source W to X. Just one single edge. That's the only way. I know it's trivial, but let's just try to interpret that. The shortest path from W to X has the weights exactly 40. That's the number. Now, what about the ancestor? You can see here, we basically do this one here. We start with the X itself. And then we kind of follow along its ancestor. In this case, it's going to be W. And then, what's W's ancestor? Neo. You can think about conceptually nil, it's not going to make any contribution. So this is one path over here. However, if you look at what's really in the algorithm, you want to take its reverse. The reverse of it, finally, the reverse of that, okay, so Rick, I'm going to put it here. The reverse is going to be exactly W followed by X. So that is the shortest path to go from W to X. I know it's trivial, just follow one edge. All right? So that's our very first example. I just want to introduce to you about the different variable, roughly how it's going to work. And on Friday, we're going to try this one here. It's not a complicated graph, but to really work out exactly how Dijkstra is going to work, it will take some efforts and focus. All right? So we'll go over this on Friday. Okay? Or maybe some other exercises as well. All right, thank you. I'll see you on Friday.